So let's continue on with part 2 of our discussion of navigating the future of AI-augmented software engineering. So now we're going to focus on this quadrant where we have conventional systems built using AI-augmented techniques, and what are some of the interesting things that arise when we start to try to do this. So let's start out with a pretty high percentage prediction. A long time ago, back in the 70s, there was a basketball player for the Philadelphia 76ers named Julius Erving. His nickname was Dr. J, and he was famous for dunks. He kind of popularized dunks. He was doing dunks before people like Michael Jordan and stuff came along. And they once said, Dr. J, why do you like dunks so much? And he said, it's a high percentage shot. You just have to jump up and slam the ball into the hoop, and you're done. You don't have to worry about it bouncing off the rim usually and taking a three-point shot that misses or whatever. So a very high percentage prediction here is generative AI is and will have a transformative impact on the practice of software development. And that's a pretty darn high percentage shot because it's already happening right now. And in fact, you can take a look at some discussions about how this is occurring. There's some links here. Like I said, I'll put the slides out. You can click on the links to see more about this. And our original study with the Software Engineering Institute talked quite a bit about what was entailed to do AI-augmented software development, the kinds of things, the kinds of models, the kinds of techniques, the kinds of tools and processes and so on that would be needed to do this. If you program, and even if you don't program, even if you program in ChatGPT or large language models in the newfangled way, these tools are being increasingly applied to improve the efficiency and the quality of software engineers, people building software and testing software and deploying software and so on, and reduce their cognitive load. And I see this quite literally pretty much every day when I prepare for my courses here at Vanderbilt that I teach on software, when I write my assignments, when I do my examples. I use a bunch of tools that are called AI coding assistant tools. And a good example of this would be something like Code Whisperer or Copilot and so on and so forth. And these would be examples of things that help you code. And we'll see some examples of that in other contexts. I will not give a lot of discussion of that right now, but when I come back for a future lecture and we have a chance to talk about how these things are being applied here at Vanderbilt in the computer science program, I'll show you lots and lots of examples of how we're building applications, we're building assignments and so on using AI-augmented tools. It's really cool. What's so fun about it is it offloads a lot of the drudgery. A lot of software development is kind of boring and drudgery, and it makes it a lot more fun because you can focus on the things that you like to do, like writing algorithms and data structures and building business logic, and not wrestling with low-level details, like figuring out what imports to include or how to make your build script or how to comment your code. It'll do a lot of that for you. Now, what's interesting about this is not everybody is equally bullish and excited about the benefits of generative AI for programmers. And in fact, there's a lot of articles. I'll show you one here. There's another one that came out a couple months ago in the Communications of the ACM. These are very famous computer scientists who, for various reasons, have decided generative AI doesn't benefit programmers at all. And here's a great article by Bertrand Meyer, the inventor of Eiffel, a longtime advocate of object-oriented programming and design, in the Communications of the ACM, which is one of our flagship communication journals and publications to get the word out to the community of researchers in computer science. AI does not help programmers. That's what he said. And if you read his article, he'll explain to you why he believes that. Now, I think he's completely wrong, but I do appreciate the fact that not everybody is equally excited about this. And one of the reasons why I think he's completely wrong is because I think he has not really thought through how to use these tools effectively. And we'll talk a bit more about that in just a second. It turns out, as with so many other things in life, if you don't use the tools right, you don't get good results. My colleague Jules White, who you've heard from in this class, gives a great metaphor where he's like, imagine Michelangelo goes up to a block of marble and he hits it one time with a hammer, and it doesn't instantly turn into the Pieta or the Statue of David. And he says, sculpting is just a fool's errand. This chisel is no good. This stone is no good. Of course, that's ridiculous. You have to work at something and learn your craft. And the same thing is true with these tools. If you don't use them correctly, if you use the wrong versions, if you don't use the prompt engineering, which we'll talk about in a second, correctly, you will not get good results. Now, to be fair to Bertrand Meyer and others, sometimes when you do use the right tools and you do the right prompt engineering, you still don't get the right results. But if you learn to use them effectively, you'll get better. And that's just the same way if you write programs in any language, in any tool. If you don't use things right, you get weird results, right? I don't know why we should be surprised about this. I actually like to call this degenerative AI. People use the tools incorrectly, they get bad results, and they throw up their hands and say, this stuff sucks. So generative AI is how you use this stuff effectively. Degenerative AI is when you use the stuff incorrectly, and then you say, oh, it's just a bunch of rubbish. So let's talk about some of the things that are challenges from a research and development point of view. This is important for people at universities, research labs, programs, government programs, and things that are trying to make the world a better place for the next generation. So one of the things we really need to work on, and you've undoubtedly seen this in this class so far with what you've done, is we need to train the large language models using better vetted input. Now here I'm focusing primarily on software, but you can imagine almost anything else. If you have crappy input, you're unlikely to get good results. So if all you train on is a bunch of spaghetti-laden code that's improperly implemented, full of security bugs, it should come as no surprise that what you'll get out as the result is spaghetti-laden code that's full of security bugs. The good news is people are getting a lot better about this, and I suspect companies like OpenAI and Google and so on and Microsoft are working very, very hard to try to train their models on better code. And there's plenty of good code out there, just not all code is good code. So you have to be discerning in what you choose. Another really important thing, and I think one of the key themes of this course, is formalizing the discipline of prompt engineering. And there's a lot of misconception about this, but let me talk through some of it, and I'll show you some examples of this in just a bit. So basically, what is prompt engineering? It can be described many different ways. I like to think about it as learning to program, using that word in quotes for reasons you'll see in a second, using natural language. And that's what you do when you interact with ChatGPT or Bard or Claude or whatever. You're programming it. You're telling it to do things, but you're not using Java or Python or C++ or JavaScript. You're using language. The language usually that we speak here is English, but you could probably use other languages as well. And what's so important about this is really, really, really important, especially for people here who are not computer science or data science majors or minors, is that the focus is on problem solving, not on traditional programming of computers, the way we've done historically. And I'll show you some more examples of this at the end of this talk, but the key way to look at this is the following. Historically, when people would come to computer science faculty like me, and they would say, I am a biologist. I want to learn how to use computation to make my research or my teaching more effective. Or I am a classical civilization professor, and I want to be able to use computation to analyze digital scans of ancient documents to look for patterns. What did we tell them? We said, great. I'm going to teach you to program in Python. I'm going to teach you to program in Java. I'm going to teach you to program in JavaScript or whatever. And people would go, well, gosh, that's an awful lot of work, and it's not really clear how that solves my problem, but okay. And then they learn to program in those things, and they find themselves with a gap between the problems they're trying to solve and the way you express the solutions in traditional third-generation programming languages like Java, C++, and so on. Not the right way to go. And one of the things we'll see here when we look at our case study at the end is by moving to a natural language-based programming model, in quotes, you're actually helping to problem solve without having to write code in the traditional way. Tremendously more productive for a lot of people, and we'll talk about that. But that's all about prompt engineering. How do you communicate with the computer with natural language? Now, what'll happen in life, and it's happening, and you're part of the vanguard, everybody in the future will be a programmer. Anybody who works with a large language model is a programmer. It's just that you're not programming in traditional languages. You're programming the LLM to do your bidding. And that's a really interesting insight. Now, some of you and some of us will learn to be programmers that way, and then we'll say, you know, this is so much fun. I want to go on and be a computer scientist or a software engineer. I'm going to learn to program with other languages that are more structured, more formal. And that's great. And a lot of you will say, the heck with that. I don't want to learn Java. I don't want to learn Python. I want to program the LLM using natural language, and that's just perfectly fine. That was not really an option until about 8 months ago. Another thing that's important here, and hopefully you've got some of this from some of the other talks, is codifying prompt patterns. Now, without getting too far into the weeds of software, so let's see, about 30 years ago, the software community understood that some people who built software had good insights about how to structure the code, and those were documentable in the form of something called software patterns. And a software pattern is a reusable solution to common problems that occur when you build software. And they provide a template to solve similar issues in other related contexts. So very important advance in software engineering and computer software development. There's lots of great books on this. If you're a CS major, you hopefully have taken the CS 3251 course, where we focus on the design patterns, elements of reusable object-oriented software patterns. There's other patterns. I wrote a whole bunch of books on this. I've written lots of papers. Software patterns are very useful because they codify expert knowledge. It's a knowledge transfer mechanism. Well, surprise, surprise, when you start programming with large language models, you're doing the same thing. You are programming, and so it should come as no surprise that they're good patterns for interacting with large language models. And in fact, Professor White and myself and Professor Spencer Smith and some of our grad students wrote a very popular paper that talks a lot about this, that talks about how to have prompt patterns for prompt engineering. It's sort of the seminal work at the moment in this emerging area. And what we do is we come up with ways of solving different problems. This is about software engineering, but you can solve all kinds of problems with these patterns. And it basically allows you to think more systematically about how to solve problems using large language models like ChatGPT and others. This is one of the things that's missing by the people who are the degenerative AI skeptics. They don't understand the patterns of effective use of large language models. I will talk not so much here, but in another lecture later about the ways we're applying this in our computer science courses at Vanderbilt. And it's remarkable how productive you can be if you use the patterns correctly. Something else to note, and this again gets off in a direction I don't want to spend too much time in here, but a lot of people think that prompt engineering is just about how to talk to the language model. And there's a school of thought, this article is somebody who subscribes to said school of thought, that prompt engineering is just an intermediate step to the nirvana where the computer just sort of reads your mind and you don't have to engineer anything, you just sort of think. It's like the classic Music Man movie with Professor Harold Hill, the think method of music. Think the minuet in G, think the solution, and it will just magically work. Nothing could be further from the truth, by the way. But leaving aside the belief that prompt engineering is just a flash in the pan because LLMs will get so smart we don't have to try to explain ourselves in a structured or coherent way, even if that was the case, there's a pile of other things you've got to do when you start actually using LLMs for real-world projects. You have to worry about things like testing. How do you make sure that the output from your LLM actually solves your problem? Software engineers wrestle with this quite a bit, very important. Dealing with the evolution of different versions of your LLMs or different LLMs. If you use ChatGPT 3.5 versus 4.0 versus Claude versus Bard, you will get different output. And when there's a new model that comes out from OpenAI, you'll get different output if you're not careful. How do you version control things across releases? Very hard issue. How do you sustain and maintain the code? There's all these engineering issues that software engineers have been thinking about for decades in the terms of writing reliable and secure and resilient software. And once people start really using LLMs in practice for more than just parlor tricks to entertain your friends, we're going to have to wrestle with the same thing. So there's a whole set of engineering aspects or quality attributes that we have to think about with respect to prompt engineering. And we're just beginning to scratch the surface on that. There's very little codified knowledge on this yet. Some other things that are going to have to happen is we're going to start rethinking how the software development lifecycle is enacted. And what we're going to see, and we're already seeing this, is we're going to increase the need for AI and other automation tool support for developers, people writing software, and other stakeholders beyond programmers. And that's something that's going to make a big difference, and we're going to start putting together lots of different pieces. You're probably already playing around with some of this here in this class, or hopefully you will by the time we get done with the semester. Tools like LangChain that allow you to group together different tools so that you don't have to expect the ChatGPT or the large language model to do all the things by itself, but when it gets to a part where it needs to do a proof for various reasons, ChatGPT isn't so good at doing proofs. It'll call out to something that's very good at doing proofs, like the Wolfram tools and so on. And so what we'll see is we'll see that the LLMs will be orchestrators for other stuff, not the executors of the work. Something else that's important is trying to capture and leverage data generated throughout the software development lifecycle. Now, if you're not a software developer or if you haven't worked in an organization, some of this stuff won't necessarily make a lot of sense. But when you start building large systems, there's a lot of other stuff beyond code. And if you take a look, you'll see that there's requirement documents, there's meeting notes that people have, there's vision statements, risk assessments, there's diagrams, all kinds of pictures of things that show the structural relationships and the interactions between the various software elements. There's test plans, there's test code, there's test scaffolding, there's all kinds of things for testing. There's ways of being able to put your software together and deploy it in the form of containers. There's all kinds of other things that you need to do as you evolve over time, like change requests and user stories. These are really the sweet spot in my mind for using augmented AI and generative AI, because a lot of these are non-code artifacts that today are handled very poorly by poor humans who can't keep track of all the information in a coherent way. Now, again, this won't make a lot of sense unless you build big software systems. When you build big software systems, there's teams of people who spend their entire careers looking at large document repositories, trying to make sense of what's in there. And this is something that LLMs are very good at because they are capable of being able to summarize and analyze large amounts of data and look for things like inconsistencies or gaps, or be able to find where things occur in a huge repository of documents. Much better, faster, cheaper than humans can do, given our limited time and our limited brains. And I'll show you more about this in some other context. All right, so that's the end of part 2, talking about the future of AI-augmented software engineering, focusing on using AI-augmented tools to build software.